So now we've got the cosine wave for the cosine form of a traveling wave is a of z comma t is equal to a p cosine of omega t minus beta z plus or minus phi. And this represents a generic traveling wave that is both spatially dependent and time dependent, or spatially harmonic and time harmonic. And if we were to draw this wave, we'd have to draw it in two dimensions, one the time dimension and the second the distance dimension. And if we picked one value for z and then plotted it, we get a sinusoidal function. And then if we picked one value for t and then plotted it, we get another sinusoidal function. I didn't draw it very well here, but the peaks and the valleys in both of these are constant. So this really should have come down like that. And that's true if the electromagnetic wave is traveling in a vacuum or in what we would call a lossless media. But not all media are lossless. In reality, electromagnetic waves, the peak value, if we were to just measure this peak value as a function of distance, the peak value would decrease as we got further along in space. And so we need to somehow modify this equation here to account for the fact that in some materials the peak value is going to decrease as we move away from the point source of radiation. And to do that, we use the exponential term. And so I'm going to just draw a plot of the exponential term, and let's make that a 1 and this a 0.3, and we'll make this number 0 and this the number 1, and I'll draw two plots. The top one might be a plot of e to the minus z, and the bottom one might be a plot of e to the minus 10z. And that's what I mean by exponential e, the natural number. And so we can use e to the minus exponential to change how fast a wave will attenuate by including that in the front half of the equation. And so we can modify our traveling wave equation to take into attenuation into account by just including some sort of exponential term. And we don't know how fast the wave will fall off. That's going to be a material property. So what we will write is a of z, you know what, I'm going to write it up here where you can see the wave. A of z comma t is equal to whatever the original peak value was here. I guess I used A0 on this slide, so I'll be consistent with the slide. A0, and I've got some sort of attenuation value. That's how fast it attenuates, and that's just saying that it attenuates as a function of position, meaning it's going to attenuate the further away from the source I get. And then we multiply that by cosine of omega t minus beta z plus or minus phi. And so by inserting this exponential function taken to a negative exponent, I've caused the cosine function to decay exponentially. That gets multiplied by the cosine term, and that'll result in this traveling wave, in this case as a function of z, that decays as it goes in z, which is really what most electromagnetic waves will actually look like. Their peak value will decrease as they propagate left to right through space. This alpha term right here is known as the attenuation constant, and it's measured in a unit called Nepers per meter, which is a little strange. Probably haven't heard of them. It's kind of similar to a decibel, which means that it uses some sort of logarithmic ratio of field quantities. And we'll explain the exact mathematical relationship between Nepers and decibels later in the course. Just right now, you just need to know that the name of that value in the wave equation is the attenuation constant, and it causes it to decrease. Now, not all materials have an attenuation constant. Some systems, we like to model them as if they are lossless. Good conductors we typically model as lossless. Vacuums are definitely lossless. And in such circumstances, the attenuation constant is just 0 in a lossless medium. And what that would mean is E to the minus 0 times Z is just equal to E to the 0 is equal to 1. So if the attenuation constant is set to 0, you just multiply the cosine terms by 1, which doesn't change its amplitude at all. And so this is the situation for any sort of lossless medium, such as a vacuum.